So, hello everyone. Today I'm presenting the dual information bottleneck framework developed by Tishby and his team, which links information theory and machine learning algorithm and tells us how information flows from the structure of deep neural network. So we will cover the information bottleneck first, and then we'll go towards the limitation of information bottleneck, and then we'll cover what is the difference in dual information bottleneck framework, what they have added. Okay. Yeah. So as we know, machine learning techniques has occupied a lot of modeling efforts because of its unique ability to learn from data without having any prior knowledge of the system. Most of the traditional system, they need some prior knowledge. They need some kind of a factors taken into account so that we can predict or so that we can make a system out of it and we can predict something out of it. But also machine learning is a black box, which takes input data and based on some cost function, it optimizes the hyperparameter, which represents the system. So information bottleneck framework presents how information get transferred from input feature to the output feature. So if you can see in this figure that there's a real world, then we experience something, and then we make an abstract concept in human minds, and then we try to model it through machine learning on traditional. Sometimes it matches with our actual mental model that it came from, and sometimes it not. So that's how it goes into iterative process. But machine learning also lacks in two areas. One is data efficiency, which is if you don't have enough data, since it doesn't need any prior knowledge, so it will not, the machine learning model will not be able to capture the data, the structure inside the data or the patterns which are coming from the data if we don't have enough data set. And the second is generalization based on the context. So if we train on something, and we can easily fool machine learning models like this picture. So if we train it on a dog, so it's very easy to fool machine learning models using the cookie and this kind of a cake. So machine learning model will not can easily be fooled. It doesn't know whether it will be. So it will just capture the hidden latent space in that and few features, and it maps to the a lot of nodes, hyperparameters, and it will classify this picture into dog or not. So that kind of a thing. So it has been a question how DNNs are able to predict nonlinear behavior with high number of nodes, which is not very uncommon because from the intuition it is possible. For example, human brain also has huge number of nodes to process the information, right? So to understand the complex structure of machine learning, information flow through the architecture of DNN can help understand how it learns the pattern from the input features. So DNN or the deep neural network extract relevant information from the input feature and encode it to a lower dimension. If you see in this figure, it takes, there are a lot of hidden layers. It takes data, relevant information from the input node, encoded into a smaller dimension, and then whenever this is required, it will decode it to get the actual information. But how can we encode it into the lower dimension? For the relevant info. Yeah. So how can we encode the whatever information is there in the input data into a lower dimension? So we can see for this from this example that if it is a sound wave and our target information is the transcript embedded, it will have much more lower entropy than the actual entire sound wave system that we have. So we can easily map it to a lower dimension, and whenever it is required, we can decode it back. So it's based on this kind of a smaller, if you can see on the top right, this is a small picture graphic that acts as an input, and we are getting a y as an output. So we are extracting features from the x and getting the relevant information to predict the y. So another thing is, if this lower dimension is too less, we'll not be able to get even the relevant information which is required to predict the y. And if it is too big, then it will pass all the information, and sometime it can go into the overfitting. Sometime it can cost us a computation and time and resources. So that's why we want to so this is a bottleneck of this entire system, which is controlling how much information is passing through input to output. So to understand and quantify the information flow between layers based on the Markov chain. So this in this figure, you can see this is the output, this is the input features that we are getting, and it is connected through a number of hidden layers. So it encodes first and then decodes to get the final prediction. So, and since it is connected through the time, we can construct a Markov chain. That information which is this H1 hidden layer is have, it will transfer it to the H2 and then transfer it to the encoder and then decode it to get the prediction of Y. So based on this Markov chain, mutual information between output and compressed representation, it will be, we can get a lesser or equal information depending on how lossy our system is. So if system is lossy, then we will not be able to pass entire information towards the encoded and decoded. And if it is lossless, then we can get actual information, which is equal to, if you see on this green box. So this X tilde is a compressed representation and I is the mutual information between output feature and the compressed representation, which will be less than equal to whatever mutual information we can, highest mutual information that we can get from input to output. So we can optimize the compressed representation by writing a cost function as this F, where I is the mutual information. This I is the mutual information between input and the compressed representation. This entire term is called as this, D is called as the distortion function, which controls how much information is getting transferred. And this beta is a controlling Lagrangian multiplier, which controls the information flow rate. So if beta is too low, beta is 0, it's a high compression, and inflow rate is low. If you can see on this diagram, if distortion is too high, the information rate is too low. And if distortion is too low, which means beta is too high, then information rate will be too high. So we want to optimize this kind of a thing where we can get relevant information as well as it doesn't cost us too much in terms of computation. This figure shows information bottleneck upper bound, theoretical upper bound, this blue line. And Peshbhai and his team shows that if we go with this methodology with the different betas, it will be very near to, depending on how much beta is, it will be very near to this upper bound. And we can actually transfer all the relevant information from input data to the output data. So we can solve this optimization problem analytically using Vallejo-Teramoto algorithm, which we can define it in terms of the probability after adding the noises in that, because right now this will be mostly single points and will not be able to define the probability function. And that distortion function in the information theory, we can convert it into a scale divergence between the compressed representation and output with the actual input and output. So if we simplify that, we can if we simplify this distortion function, we can get this mutual information here. And again, we can get an optimization problem in terms of mutual information. So this term represents the mutual information between input and the compressed representation. And this term represents the compressed representation and Y. And we are minimizing this entire cost function, which means we are maximizing the information shared between output function and compressed representation. That is our main focus point. And at the same time, we want to compress our we want to extract the relevant information only. So mutual information between input and the compressed representation should be very less. Yeah, so if you can look at the figure, this figure, x-axis is the information between. So this T is the hidden layer, and this x-axis represents the mutual information between input feature and the hidden layer, and the y-axis represents the mutual information between output and the hidden layer. And these dark lines represent different hidden layers in the system. So this one at the top right corner represents the closest to input, and this one represents the farthest from the input. So if you can see, we have a lot of information about input and output at the first layer. And as we go forward, this is like obvious that we will not have that much of information. So if we start from this point, the lower point, we will not have too much information about X, as well as not too much information about the output. But as we train this model, so these color represents the epochs that we are training. So as we train, it learns the patterns which are there in the input feature for some time. And at this point, there's an interesting thing happen, and it decreases. It tries to compress the relevant information, or we can say in other words that it is trying to extract only relevant information from the input feature. But at the same time, it is learning it is only extracting the relevant information, so that it is increasing in the y direction, but decreasing in the x direction. So this direction it is decreasing, and on the y direction it is increasing. So for this figure, it assumes, our model assumes that our training data has all the characteristics and all the representation. It's a good representation, a statistical representation of the entire data set. So that's why we are getting this thing. And with the different input models, different data, we can get a different shape, but it will still be something like this. It will increase for first initially, and then it will compress and extract the relevant information from the input data. But what happens if we have a finite data set? So if you can see on the left hand figure, it will again start with the same mutual informations, but initially it will increase, it will learn the pattern, and after a while, if data is limited, it's not the representation of entire data set. It tries to decrease in both the direction. So it will kind of overfit the model, and it will decrease in the x direction and the y direction. So this problem can be possible with a finite data set. So that is the limitation of information bottleneck, that mutual information is insensitive to complexity of function and invariant to any random perturbations, and it cannot capture the structure of X. So just using the information. Yeah.
So Tarun, these are results shown on test data, I assume. Is that correct?
Yeah. Yes.
That's why you're getting the decline in I of TXY, TY. Okay.
Yes. Yeah. So this is kind of going into a overfitting regime. So why it is starting to rise here? Because it is getting the major patterns in the data, and after a while it tries to learn the nuances in the data, but by doing so, it kind of overfit the entire system. Yeah, so dual information bottleneck breaks the complete distribution knowledge assumption of information bottleneck. So it adds another bottleneck as y tilde here. This entire Markov chain can be treated as training phase and predicted phase. So this is kind of a training phase and this kind of a predicted phase, as said by Fishby. So it will capture the structural aspect of the solutions. And if this is a large sample space, so while adding this y tilde, if we have large sample space, it will give the solution or the prediction as same as the information bottleneck. But it kind of trying to do, so if we have limited data sets here, it tries to be a bad compressed version of that thing. And then if we try to use our input data with this compressed version, we will get something very different, very distorted predictions from this entire thing. So including how much distorted it is, the prediction whatever prediction we are getting from the finite data set, how distorted it is from the actual prediction, it is trying to get this term also into the system so that it can get at least some sense of how and optimize that distortion down the line. So again, new distortion optimization can be written as following equation. Again, it's the same thing. Distortion function includes both the x tilde and the y tilde, and this distortion function based on the dual information bottleneck can be simplified as this green box thing here, where before it was only one term here, and now it has three terms. Mutual information between compressed representation and the prediction we are getting from that, mutual information between input and the output presentation that we are getting, and there is a distortion from those two systems. I mean, the actual predicted version versus the prediction that we are getting from the finite set. So as we can see, this both term vanishes when x tilde is sufficiently statistics on that, and this will behave like a simple information bottleneck. So again, we can solve it iteratively using the BA algorithm as same as the information bottleneck we did. And then Satish Bhai gave a few examples. So this problem is very small. They started with 5 input. Yeah, so it was a 5 input x and 1 binary output y, which is 0 or 1. So if you can see, focus on this left figure, this x-axis represents the beta, the Lagrangian multiplier, and then the y-axis represents the probability of y is equal to 0. So if you can see here with the dual information bottleneck, so this one is the dual information bottleneck line, and this, if you can see my cursor, this one is the information bottleneck lines. So if you can see for the two different things that we can get out of it. First is at the larger betas, which means larger information is passing through the model. So at the larger betas, both the system behaves similarly, but at the smaller betas, if we take any smaller beta, that we can say that we have more information about the system from the dual information bottleneck system. So at the lower beta with the higher compression, also it gives a bifurcation well before the information bottleneck. And you can also see from here that we have more information about the system, relevant information about the system at any beta, which is very in the lower region. So this blue curve is a dual information bottleneck, and then this red curve is information bottleneck. So at any beta, if you draw a line, vertical line here, you can get more information from here. And this inside plot is showing how different. So this x-axis and y-axis is dual information bottleneck and information bottleneck. So more or less, those are behaving same for this smaller problem, but it can behave differently for the larger problems. And also, if you see the benefits, these are the benefits of dual information bottleneck over information bottleneck. So if you see the iterations to converge the system at any beta, the dual information bottleneck have a very less number of iterations to get it to converge, versus information bottleneck takes a lot of time and a lot of computation efforts to converge it. And as we see, we are going to higher betas, it becomes similar. It behaves very similar, the dual information bottleneck and information bottleneck. So going ahead, we can also preserve the structure of dual information bottleneck using the exponential family and class of parametric distribution. We can define this probability distribution in terms of exponential families, and we can get all the parameters, analytical parameters of the input data that we have. I'm not going into details with this. We can, it's in the detail in the paper. So the next thing they did is variational dual information bottleneck. Variational means so initially they were doing it on the autoencoder and decoder. Then they tried it with a variational autoencoder and decoder, which means to add a statistical and parameters to the data and have a probability distribution, and then get the information, mutual information between different things. So these colors defines. So this purple line is defined as the variational dual information bottleneck, and this green blue is the variational information bottleneck, with darker colors means the lower betas, and the lower colors, the lighter colors means the higher betas. As you can see, again, it's the same inference we can get at lower betas. Lower betas, we have more information about the system as compared to the information bottleneck, but at the higher betas, we can it behaves similarly. So here also, if you see the accuracy with the training examples, it behaves almost similar for that smaller problem. But again, they didn't try it for the larger problem, what happens there. But that's their argument that it should behave similarly to this. And if you see the compression at the lower betas, it compresses the mutual information between input and the compressed representation, and at the higher betas, because since all the information is passing through the bottleneck, so it is not compressing too much as compared to the lower betas. So yeah, that was the overall information bottleneck and dual information bottleneck in like very brief. If you have any question, we can discuss.
Can you go back, Tarun, and explain the change in the cost function?
Yeah, so this one.
Previously, we were minimizing I x tilde minus beta I x tilde y.
Yeah, still the y.
So what's the change now?
So yeah, initially we were trying to optimize the representation, the compressed representation and the output, and we are trying to get it higher so that we can get the maximum information out of the compressed representation about the output. Now, since we have limited the input set, so we have very finite data set, so our compressed representation will not give a very accurate output representation, right? And it will distort from the actual or the observed output that we are trying to get. So that's how they compute these three terms came into existence. So this is the distortion function between the predicted representation versus the actual prediction that we want to get. And these two terms are the mutual information between the compressed representation and the predicted output set, which we are trying to lower it, since it distorts because of the finite data set. It is distorting the actual output representation that we want to get. And at the same time, our input data has more information about the prediction. So we are trying to increase this term.
But what is y tilde? It's still not clear to me.
Okay. So y tilde is the actual, not actual. So y tilde is, so once you train it, so depending on your output and input, you will have the compressed representation. But if you have a finite data set, you will not have a good compressed representation.
Yep.
So whatever input we have from this distorted compressed representation, what will be the output function, output prediction that we get?
Okay, so y tilde is the simulated values generated by the model.
Yeah. Yeah.
Okay.
Y tilde is a simulated values.
All right. So go back to, so what is I x tilde y tilde? Why is that not 1?
Why it is not 1?
I mean, y tilde is generated using x tilde, right?
Yeah.
So presumably I x tilde y tilde is somehow maximal if x tilde was used to generate y tilde.
But probably that is from the testing set. Oh yeah, right. You're right. Actually, this should be actually 1.
Well, yeah, I don't know if it's 1, but whatever the maximum value is.
Yeah, yeah, whatever the maximum is.
And then I x y tilde, why is that also not 1? I'm still having some. I'm sorry. X is compressed to x tilde. Okay, so x to y tilde need not be 1 because you may have lost some information when generating x tilde.
So I think this x tilde is generated from the output function, the accurate output that we want to get. And this y tilde is from the everything is already done. X tilde, we have x tilde. And now what will be, because of this loss, information loss and everything, what will be the prediction that we get from that x tilde?
Also, the term B is the Kullback-Leibler divergence between probability of y tilde given x and probability of y equals y tilde given x. I guess I'm just having some difficulty figuring out how you actually calculate all these quantities.
So this probability is where y is equal to y tilde given x, the joint probability of that. Whereas this probability is whatever y tilde we are getting given x.
But since x was used to generate y tilde, since y tilde is the simulated value, that's what I'm confused about. If y tilde is a simulated value, then the probability of generating that simulated value is presumably 1. Of course, it need not be, it could be a stochastic model, I guess.
Yeah, so to that will be a fixed point whenever there's a simulated value. So that's why they add noise, Gaussian noise in that to get a probability distribution across around the simulations.
I mean, if the answer is simply that they add Gaussian noise to the simulations and that improves the learning, that's a very different message that I take home. Right. Because basically that's the same as saying if I add noise to my model, I prevent overfitting, and so my result gets better. In which case, I'm not
But at
sure
the
why.
same time, oh, sorry. So I was saying at the same time, so they have also done this on the variational auto encoder decoder. So this one doesn't include a Gaussian noise, but variational encoder decoder, it generates its a statistical parameter inside the model and then add at every point to get a distribution. So even with that dual information bottleneck system, they say that it is doing better, which you can see with a very smaller example. So it is
Sure.
better. It does better with the smaller betas as compared to the information bottleneck.
Can you go back to the regular information bottleneck? One more. Sorry, forward. And here, yeah. So here I understand you have X, which is your input data, you have X tilde, which is your compressed input. And you're checking to see, you're trying to compress it as much as possible, which means you're trying to minimize Ix X tilde. That makes sense. And then you're trying to maximize the information, mutual information in X tilde and Y being the observed value, and X tilde being the compressed input. And that makes sense. So you maximize Ix tilde Y, and if you increase beta, then that gives a stronger and stronger reliance on maximizing the information between X tilde and Y.
Hoshin, can I just ask, that compression that you want to compress X as much as possible to get X tilde, is that without losing any information? Or
so presumably, if you can compress it without losing any information, then that term remains 1.
but
Or
that's not,
let's say the maximum is 1.
Okay, so that's not an assumption here,
though. So the idea is that X may contain information that is not relevant to Y. Okay.
Okay.
So when we go from X to X tilde, we want to preserve only the information that's relevant to Y, so we can get some compression, which means Ix X tilde can go down.
Okay.
And at the same time, we want Ix tilde Y to go up. So we want to preserve all the information that's relevant to predicting Y. So in principle, Ix tilde Y could be 1. Let's say it's perfect. Yeah. And so you got something minus beta times 1. And if Ix tilde is, if Ix tilde Y is 1, then we're just basically compressing the input. So as long as we keep compressing the input, as long as we don't affect the ability to predict Y, we can just keep compressing the input. We just keep, so we get a more and more compact model. Now we get to a point where Ix tilde Y starts to reduce. Yeah. So now if that goes down, then because you're subtracting it, the joint thing starts to go up again, right? Because you're subtracting a smaller quantity. So you get this sort of trade-off. That's the basic idea here. So ideally, you would just compress X to X tilde only to the point where you don't lose any information about Y. But in general, you could keep compressing it, and then you would lose information about Y.
So I'm thinking about like in a real world scenario, that is what we have. Is we have a it's not complete mutual information. So I guess I'm trying to think of that X tilde as like a data source that isn't perfect from the real world.
Correct. Right. So normally you could just build a model between X and Y, and you would just maximize the mutual information between X and Y. Forget about the compression, right? That would be the maximum that you could get. That was the previous slide. And so now we're compressing X to X tilde through some latent variables. And so we're hoping to get the most compressed model we can, but while not losing any of the information that's present in X about Y. So this is the theory, assuming the later part of what Tarun said is, okay, now what happens when you actually apply it to limited data sets? So this is assuming perfect data, right? Complete data. Okay. Now I'm trying to understand where the dual part comes in, because now they're saying that you can in principle overfit to Y if Y is insufficiently representative of the actual, right? So it's not clear to me here what is. So now I'm trying to understand what is Y tilde. Is Y tilde a subset of Y? Is it a compressed version of Y? What exactly is Y tilde? That would, if I could figure that out, that might help. So maybe we could go back to that slide now, Tarun. The one where you showed the chain. Yeah. So X is being compressed to X tilde, and X tilde is being used to generate Y tilde. And then the next line you say Y tilde is the same as Y, but distributed differently. That's the statement I don't understand.
So it says that it's a simulated version, but it can, because it's coming from a overfitted X tilde, overfitted model, it will be same as Y, but distributed. The distribution will be completely different for Y tilde.
So this makes me think of streamflow forecasting, where we take the sorted streamflows, simulated streamflows, and the sorted observed streamflows, and then we look at them and we say, hey, these things are not distributed the same. We want them to have the same distribution as opposed to having the same location by location matching. That's what it sounds like to me, just reading the sentence without digging into their thing. But you're basically, I agree, you're basically saying that the model is generating a simulation which is not coming from a distribution that looks different than the distribution that the original data was generated from somehow.
Why wouldn't they express like an upper, like is there like a asymptotic approaching the original distribution? Like, is it guaranteed not to be distributed the same?
Say that again, please, John.
Why can't it be distributed the same? Have the same distribution?
So presumably, if X tilde is overcompressed, then it will not generate a Y, or Y tilde in this case,
okay,
which has the same distribution as Y.
And that's why we are getting at the higher beta dual information bottleneck, and information bottleneck behave same, because all the information is transferring from that bottleneck, and then now X tilde is also having relevant information.
Okay, so that helps a bit. because it's saying not only are we trying to maximize mutual information, but we're also trying to maximize distributional consistency. That's what I'm interpreting right now. I'm not saying that's what they're saying. So mutual information is kind of like a point-by-point matching. And the other term sounds more like a trying to preserve the statistics of the distribution as accurately as possible. So I suppose that makes sense. You could it's like when we minimize mean squared error, we say mean squared error has two terms, the mean squared plus the variance squared. And you could reduce the variance term, but you could increase the mean, which means you're starting to get a distributional mismatch, right? So the bias variance trade-off kind of thing. So it seems like it has that kind of flavor to it. It still doesn't explain to me how specifically they're computing this Kullback-Leibler divergence term. So that would be interesting to know. Yeah. And it still doesn't explain to me why I x tilde y tilde is not 1 or whatever. Although maybe the fact that what Tarun said, which is that they're adding a noise distribution on top, might be the reason for doing that. Yeah. So when you add the noise distribution, you can increase or decrease the noise. If you increase the noise, that mutual information will go down. And so maybe it helps with identifying how much noise you have to add. Because I think, I mean, you guys have also read the literature. I got the impression that there's at least some support for the idea that adding noise to your model output before training actually helps to reduce overfitting, which would make sense because, yeah.
Yeah, and that's not it's extremely common and that's well known, right?
Yeah. But this sounds like there's two components to it. One is the adding of the noise, and the other is this use of a different metric to help stabilize the result to prevent overfitting. One being adding noise, another being checking for distributional consistency, whatever that means in this particular context. But that may not be dissimilar from what we do when we say we're going to add to our metric a regularizing term, which is to match take out the time order, and we just match the distributions between the observed and simulated properties, quantities, yeah. Because that prevents overfitting too, because it prevents you from matching specific data points. Right? So it's like a weaker way of doing mean squared errors. You sort the data and you just do the mean squared error on the sorted data. So you can't overfit the data, but it's going to be a weaker thing. So maybe adding both terms actually helps. Yeah.
We can also think this term as so y tilde is our simulated representation, how much information it shares with the over compressed version versus how much information it shares with the actual input data and the difference of that. So it kind of gives a feeling that how much information is transferring from that over compressed version.
Yes.
Actual relevant information. And then this represents, maybe we can do a little bit more digging, but yeah, this is how much distortion happened in the distribution.
Yeah. I mean, the part that confuses me is this probability of y tilde given x and probability y is equal to y tilde given x, because that's given x, whereas when I talked about the total distribution, that's not exactly the same as given X. It's given X as a whole, not given X as an individual, point by point values. But, yeah.
I have a question. I get this idea of X approaching, or sorry, of the A term disappearing
Yes,
as X approaches X tilde.
makes sense.
I get that, but I'm trying to think of like what happens in the opposite direction. Like what I'm trying to think of the opposite extreme. How to interpret that? Like what would that represent? X diverging more from. Is that going to be like too much compression and we're losing information about why?
Yes.
Okay.
Yes, that's what we typically call distortion, is when you overcompress. So X tilde diverges from X in terms of information capacity, quantity, and that's what the D is called, the distortion. Yeah, it's up at the very top there, D dual X tilde. Yeah.
Okay, thank you.
But that helped. So we want A to go to 0, and we want B to go to 0 too. So the part that I think we're missing in our understanding term is exactly what is this B term, right? If we could understand that, then I think we pretty much probably have an idea what's going on here. So
Yeah.
how is B computed? Yeah.
Yeah, in the paper, it's mostly they don't clearly explain what is this term physically means,
Yeah.
but they go into the maths and then they just solve it, everything.
Right. What year was this paper?
This paper was, I guess, 2020. Yes.
Okay.
Let me double check it. Yeah, it's 2020.
Okay. I wonder if it would make sense to drop him an email, Tarun.
Yeah.
Just saying, hey, we've got a group, we've been studying your papers, and we had a question about this particular term, how exactly that's computed, how to interpret it. Yeah. Never know. I mean, Tishby's group is one of the people that we're actually hoping to invite somebody out to the workshop. So might help to just send out a contact and feel them out and see how responsive they are.
Sure.
Cool. So to summarize, see if my understanding conforms with yours, Tarun. The idea is that if our data set is fully informative about the process, whatever that means, is distributionally consistent with the overall set of processes that are going on, it's fully informative, then the standard information bottleneck approach theoretically is the correct way to approach the problem. It tells you how to compress your data, build a model, which summarizes your relationship between X and Y in the smallest possible way, while preserving everything you need in order to do predictions. Dual information bottleneck came about because if you're using data that is not fully completely informationally complete, that using standard information bottleneck could result in a sort of overcompression or a distorted model, which would then not perform well on valid or test data or validation data, because it would overfit to that smaller data set, to that less informative data set. And so the idea is to try to counteract that by adding additional terms to the cost function, which help to mitigate that or reduce the probability of that happening, something like that. Does that make sense?
Yes, yeah.
Okay. Okay. Did they run experiments? I think you showed us, but with progressively reduced sizes of data. And
Yeah, so
what
they
happens?
used only one example in there. That was like very small example with 5 input and 1 binary output.
Okay.
There were other
But
papers you were showing. I remember you were showing that a while ago, that there are controversies to use that method to get information, that kind of a thing, with a bigger data sets.
Sure. Yeah, the problem is, how do you compute mutual information in those?
Yeah.
What's a consistent way to do it? Could you show us those figures where they reduce the data set again, so we can see what's going on?
Yeah, sure.
So which is referring to the size of the data set?
So these different points are the 5 input which we are getting. So since beta is too low, you will not be able to bifurcate between these things. Different inputs is giving you different output, because
Okay.
not all the information is passing.
But this is changing beta. This is not changing the length, the size of the data set.
Yeah, so they didn't use any other data set. They showed only this one example to show them dual information bottleneck does better than. If you see on this right hand side figure, they show that at a lower betas, information bottleneck, dual information bottleneck does better than with any beta. If you draw a line here, vertical line.
Okay. But do they explain how they constructed this data set relative to the original data set?
No, they just take a very sample, small problem and they just show it. It's mostly a theoretical framework.
Oh, see. Okay. So beta is large means you preserve as much information about the output as you possible. Beta small means you preserve less and less information about the output. I see. So small beta means more compression of x to x tilde. Okay. And so the bifurcation occurs when you put in a strong enough beta that you preserve now the okay. So your first dashed line on the figure to the left.
This one is dual information bottleneck.
Right.
And this line is information bottleneck.
So it bifurcates earlier, meaning that it learns faster from the data. Okay. All right. Okay. So even though it's more compressed, it's compressing in a way that is more consistent with the information it needs to learn about the output. Okay. That sort of makes sense if you think about it, because if you are saying that I have to maximize mutual information, but I also have to preserve distributional properties, then I'm adding additional constraints on the learning process. So in principle, I can't maximize mutual information while giving some wildly different distribution, forcing. I'm creating sort of a condition under which the learning has to stay a lot closer to the properties I want. Okay. All right, that helps. Anybody else have any other thoughts or questions? My take-home message is we're adding regularization.
Right. They are just changing the cost function, and then from the cost function, they are getting the structure out of it.
Yeah. They're just regularizing the problem a little bit better.
Yeah.
Luis?
No, the same. Finally, this is my my message. It's kind of regularization, because what I was thinking is that in general, this is working because we have the issue that the Y in some way has more information than X, the original one, because we are always thinking that we are going in one direction, that this X has more information than Y. But in the other case, when the data set is not really in some way, Y has more information. For that reason, they are trying to create this constraint in the other direction.
Sure, makes sense. Manuel, Johan, any thoughts?
No.
All right, sounds good. Manuel?
No, I came back to your comment also on how how do you actually calculate mutual information?
Yeah, okay. Yeah, Manuel and I are actually taking a look to see if we can figure out a better way to calculate mutual information from continuous data. Because normal methods require you to do binning and all of that. So we're hoping to make a little bit of progress on that. And Manuel is planning to visit us in February, I think, somewhere around there. Yeah. So
there
okay.
There were other papers that I have came across using this dual information bottleneck. So this they used it on autocoder encoder.
Okay.
But I've seen the same theory applied to the CNNs and the regular DNNs and then other things. So they use different techniques to calculate mutual information. One was, I don't remember the name, but there was one technique where they didn't use any probability distribution. They were directly calculating mutual information from the single points using eigen values, eigenvectors, something like that. I can dig into that and share if that helps.
That would be great. I do think if we could have a little discussion about what's happening with people figuring, because it's a nice theoretical construct, but it's so difficult to compute that it'd be interesting to understand what progress other people have made. I know there's something called hashing, which people use as an approach. I haven't dug into it very much.
So this is just one bottleneck, but I've seen people who are using a lot of bottlenecks. Every hidden layer, there is a bottleneck, and they are trying to optimize this entire structure. So there were very interesting applications on this.
Sure. Yeah, I mean, deep learning, presumably the way it worked was you trained your first hidden layer to maximize mutual information about the output, and then you trained your second layer, and then you maximize keeping the first layer constant, and then the third and fourth, and so on, right?
Yeah.
And then after that, after you pre-trained all your layers, then you did the full thing. So it's interesting to ask what's happening as you move down those layers. The figure you showed that the mutual information between the input and the compressed representation diminishes as you move from first layer towards the end, right? Which would sort of make sense. The question is what's happening to I x tilde y as you move in that direction also, right? And you would want that to presumably stay constant or increase.
Right.
I mean, it couldn't. No, it cannot increase. So you would want it
Yeah,
to at
it
least
will
stay
be
constant.
constant. It will be constant because X and Y are already fixed. It
Right.
would be constant.
And if it starts to go down, then you know you're in trouble. Yeah. Okay. That's interesting. Yeah. Okay, lots to think about. I should probably go. Thank you for doing that, Tarun. That was very, very helpful. Yeah, be nice to send out that email and see if we can get any response. Find
Sure,
out.
sure. Yeah, I will.
And if you could send me that thing about the mutual information
Yes.
method, we can
Sure.
dig into that.
Yeah.
All right.
Okay.
Bye, guys.
Bye-bye.
Bye.